Welcome to another deep dive, everybody. Today, we're going to be talking about the world of quantum computing, and specifically how those tiny particles that we hear so much out, electrons and photons, are actually used in these incredible machines.
Yeah, it's really about unlocking a whole new level of computation,
Yeah,
by harnessing the strangeness of the quantum world.
exactly. Um, but before we get to quantum computers, I think we need to understand the stars of the show. So let's start with the electron. What exactly is an electron, and what's all this talk about spin?
Okay, so think of an electron as one of the fundamental building blocks of matter, like a tiny Lego brick that makes up everything around us. It has a negative charge, and one of its key properties is something we call spin.
Okay, so it's not actually spinning like a planet, right?
You got it. It's
Right.
not really spinning like a planet. It's more like an inherent property. It's a kind of angular momentum. A useful way to visualize it is to imagine the electron spinning. But in reality, it's a purely quantum characteristic.
This is more of a quantum thing than a physical spinning thing. And this spin is important for quantum computing. How so?
This is where it gets really interesting. Electron spin is quantized,
Okay.
meaning it can only exist in specific states, like up or down. Think of a light switch. It's either on or off, not somewhere in between.
Gotcha. So no dimmer switch for electron spin.
Exactly.
It's either spin up or spin down, and that's it.
Precisely. And to really grasp this concept, we need to look at a groundbreaking experiment, the Stern-Gerlach experiment.
Okay. The Stern-Gerlach experiment. Sounds intimidating. Break it down for us.
Imagine shooting a beam of silver atoms through a magnetic field. This field isn't uniform, it's stronger at one end than the other. Now, if these atoms were just little magnets with randomly oriented spins, we'd expect them to spread out over a detector screen in a continuous blob, like a shotgun blast.
Okay, makes sense. So what happened that made this experiment so important?
Instead of a continuous spread, the atoms landed in two distinct bands, one deflected up, one down. This blew everyone's minds because it showed that the spin wasn't random, it was quantized.
Whoa. So like our light switch example, only two options, spin up or spin down, and the experiment proved it.
Exactly. And this is crucial for quantum computing because we can use this property of electron spin, this up or down, to represent information. It's like our zeros and ones in classical computing, but with a quantum twist.
Okay, I'm starting to see the connection here. So we've got these electrons with their quantized spin. But how do photons fit into all this? They're particles of light, right?
That's right. Photons, while different from electrons, can also be used as qubits, the building blocks of quantum information. But instead of manipulating their spin, we use a different approach. Think beam splitters and interferometers.
I remember beam splitters from physics class. They split a beam of light. I'm having trouble picturing how that relates to quantum computing.
It's all about the quantum strangeness that emerges. Imagine a barrier with holes like Swiss cheese placed in a pond. When water waves hit the barrier, some pass through, some get reflected. That's similar to what happens when a single photon hits a beam splitter.
Okay, so the beam splitters like our Swiss cheese barrier, directing photons in different directions. But where does the quantum weirdness come in?
Well, even though we're sending single photons, individual particles of light, each one acts like it's taking both paths simultaneously.
Hold on. A single photon is in two places at once. That's pretty mind-boggling.
That's the magic of superposition. Until we measure the photon, it's in a state of being both transmitted and reflected. It's like that spinning coin in the air. It's both heads and tails at the same time until it lands.
Okay, so a beam splitter creates this superposition, which is a key element in quantum computing. But you mentioned interferometers. What are those? And how are they different from the Stern-Gerlach experiment we discussed earlier?
That's a great question. While both the Stern-Gerlach experiment and interferometers demonstrate quantum phenomena, they operate in different ways. The Stern-Gerlach experiment focuses on the intrinsic spin of particles like electrons, sending them through a magnetic field. Interferometers, on the other hand, manipulate the path the photon takes, revealing its wave-like nature.
I'm really curious about these interferometers now. Can you give us an example of how they work?
Absolutely. One of the most famous interferometers is the Mach-Zehnder interferometer. It uses two beam splitters and mirrors to create a situation where a photon takes both paths at the same time, leading to some surprising results.
Okay, you've got me hooked. Tell me more about this Mach-Zehnder interferometer and these surprising results.
We'll delve into that fascinating device in the next part. It's a perfect example of how these seemingly simple setups unlock some of the deepest mysteries of the quantum world.
So you were about to tell us about the Mach-Zehnder interferometer
Right.
and how it demonstrates the strangeness of quantum mechanics
Right.
using photons.
The Mach-Zehnder interferometer takes the beam splitter idea
Okay.
a step further. It uses two beam splitters, cleverly arranged with mirrors, to create two possible paths for a photon to travel.
So it's like setting up a maze for a single photon to navigate.
Exactly. Now here's where the quantum weirdness kicks in. A single photon enters the interferometer, hits the first beam splitter, and guess what it does and choose one path or the other? It enters a superposition, taking both paths simultaneously.
It's like the photon is in two places at once until we try to figure out where it is.
That's a great way to put it. And now these two paths eventually recombine at the second beam splitter, and this is where things get really interesting.
So the photon, being in this superposition state, arrives at the second beam splitter from both directions simultaneously. What happens then?
You might expect that since the photon took both paths, there's a 50-50 chance of detecting it at either of the two detectors placed at the output of the second beam splitter, like flipping a coin, right?
Yeah, that seems logical.
But here's the kicker, that's not what happens at all. The results of this experiment are anything but ordinary.
Okay, spill the beans. What do we actually see happening in this Mach-Zehnder interferometer?
Instead of a 50-50 split, we find that only one detector clicks every time. It's like the photon knows beforehand which detector to trigger and only takes the path leading to that specific detector. But remember, this is a single photon taking both paths simultaneously.
Whoa, now that's definitely counterintuitive. How do we explain that? Does the photon somehow know where to go?
The answer lies in a phenomenon called phase shifting. You see, the beam splitter isn't just passively splitting light. Depending on which side of the beam splitter the light enters from, it can actually shift the phase of the light wave.
Phase shifting. That sounds a bit technical. Can you break it down a bit more?
Imagine a wave on the ocean. It has peaks and troughs, right? A phase shift is like taking that wave and shifting it so that the peaks now align with where the troughs were before.
So it's like sliding the wave along itself, changing its starting point.
Exactly. Now, in the Mach-Zehnder interferometer, one of the paths the photon takes undergoes this phase shift while the other one doesn't.
Okay, so one path gets phase shifted, the other doesn't. How does that explain the weird detector behavior?
Well, when the two paths of the photon recombine at the second beam splitter, they interfere with each other.
Like waves crashing into each other, creating bigger waves or canceling each other out.
That's the idea. And because one path was phase shifted, the interference pattern is such that the probability of detecting the photon at one detector becomes 0, while the probability at the other detector becomes 100%.
So it's the interference of these two paths, one phase shifted and one not, that forces the photon to be detected at only one specific detector.
That's the essence of it. And this highlights a crucial point. Even though we're talking about a single photon acting like a particle, we have to consider its wave-like properties to explain the interference. It's this wave-particle duality that's at the heart of quantum mechanics.
All right, I think I'm starting to grasp how this Mach-Zehnder interferometer works. It's certainly a lot more complex than the Stern-Gerlach setup.
It is indeed, but both demonstrate different aspects of the quantum world. The Stern-Gerlach experiment reveals the quantized nature of particle spin, while the Mach-Zehnder interferometer highlights the wave-like nature of photons and how interference plays a key role.
So how do both of these connect to the big picture of quantum computing?
That's the million-dollar question. By manipulating electron spin or cleverly using beam splitters and interferometers like the Mach-Zehnder, we can harness these quantum properties for computation.
So we're basically taking advantage of these bizarre quantum phenomena to process information in a completely new way.
Exactly. The fact that these particles can be in multiple states at once, that superposition, is what gives quantum computers their power. We can then manipulate these superpositions using things like phase shifters and interferometers to perform calculations in ways unimaginable with classical computers.
It's mind-blowing how these tiny particles, with their strange behaviors, are opening up a whole new realm of computing. But I have to ask, are electrons and photons the only players in this quantum computing game? Or are there other quantum particles we could use? Are electrons and photons the only particles we can use for quantum computing? Or are there other quantum particles out there that could be harnessed for computation?
That's a fantastic question. And it really highlights how quantum computing is still in its early stages. While electrons and photons are the most common types of qubits being explored, Researchers are also investigating other particles and systems.
Oh, wow. So there's a whole universe of quantum possibilities still out there.
Absolutely. For instance, some scientists are looking at what they call trapped ions,
Okay.
where individual atoms are held in place using electromagnetic fields. The energy levels of these ions can then be used to represent quantum information.
So instead of using the spin of an electron, we
Right.
can use the energy levels of a trapped ion to create a qubit.
Precisely. And there are even more exotic approaches, like using superconducting circuits, which leverage the strange behavior of electricity at extremely low temperatures to create qubits.
Wow. It seems like the possibilities are endless. It makes me wonder, what's the advantage of using one type of qubit over another?
That's a great point. Each type of qubit has its own strengths and weaknesses. Some are easier to control, while others are more stable or can perform operations more quickly. It's a bit like choosing the right tool for the job.
So it's not just about finding any quantum particle, it's about finding the right one for the specific task we're trying to achieve.
Exactly, and that's one of the exciting challenges in the field of quantum computing, figuring out which qubits will ultimately be the most practical and scalable for building powerful and reliable quantum computers.
It's incredible to think that we've gone from understanding the bizarre behavior of tiny particles like electrons and photons to actually using them to build computers that operate on entirely different principles.
It really is a testament to the power of human curiosity and ingenuity. We started by asking fundamental questions about the nature of reality, and those explorations have led to a technological revolution that could reshape our world.
Well, this deep dive into the quantum world has been a mind-blowing experience. From electron spin to the wave-particle duality of photons, we've covered some truly amazing concepts.
It's been a pleasure exploring these ideas with you, and I think the biggest takeaway is that the quantum world is full of surprises. And the more we learn, the more we realize how much more there is to discover.
And who knows what other strange and wonderful particles might be out there just waiting to be harnessed for even more powerful and transformative technologies.
Exactly. The future of quantum computing is wide open, and it's a future we're creating right now, one experiment, one discovery at a time.
Well, that's all the time we have for today's deep dive into the world of quantum computing. Hopefully, we've left you with a sense of wonder and excitement about this incredible field.
And perhaps you'll be inspired to continue exploring the quantum realm on your own. There's a whole universe of knowledge out there waiting to be discovered.
Thanks for joining us, and until next time, keep on learning.